Promax Combustion. Fire done safely.
Hello everyone, and welcome to Promax University. This is the third module in our Combustion 101 series discussing the importance of emissions and their respective environmental impact. Before we dive into too much detail, it's important to point out that all of our presentations are geared towards industrial combustion applications. Although combustion emissions are an extremely broad topic, we're going to centralize our discussion around three main points. 1. Current provincial regulation. 2. Emissions groups and their constituents. And 3. Combustion efficiency. Emission regulations are constantly evolving. Obtaining accurate measurements is sometimes difficult, and enforcement of regulation is all but non-existent. However, there are specific guidelines depending on geographic location. For Canada, NOx production is limited to 75 parts per million, or ppm, CO limited to 400 ppm. This applies regardless of burner capacity. For Quebec, NOx is limited to 50 ppm and CO to 400 ppm. These limits apply only to combustion systems rated above 10 million BTUs per hour. The City of Montreal has imposed even more stringent limits, with NOx limits of 35 ppm and CO limits of 400 ppm. Again, this is applied regardless of burner capacity. Emissions can be divided into three main groupings: particulates, unburned volatiles, and various oxides. Particulates are exactly as the name implies, particles that are released into the atmosphere. Technically, particulates refer to particles measuring between 2.5 and 10 micrometers. They are normally associated with soot formation, incomplete combustion, and liquid or solid fuel combustion. Unburned volatiles are also exactly as the name implies. These are combustible materials that exit the combustion system via the stack but remain unburned. It is important to note that this includes more than unburned fuel caused by incomplete combustion. There are several processes that emit volatile compounds that are also considered as integral system emissions. Unburned volatiles are considered as among the most offensive greenhouse gases. Oxides can be divided into three separate compounds: sulfur, carbon, and nitrous oxides. These three have proven to be the major modern-day concern regarding emissions and their respective environmental impact. Particulates can most easily be visualized using a forest fire as an example. We've all seen the video streams of large-scale forest fires generating towering plumes of smoke and raining down burning ambers. Both the smoke and the ambers are examples of particulates being formed during the combustion process. For lack of a better word, dirty fuels and incomplete combustion are major contributors to particulate generation. Societal conversion to cleaner fuels and advancements in scrubbing technologies have all helped lower the amount of particulates entering the atmosphere. Since 1990, we have witnessed a 1/3 drop in measured particulate concentrations, even with the boom in energy consumption we have witnessed around the world. Before discussing unburned volatiles, it is important to understand the impact of the greenhouse effect. The thin atmospheric layer that envelopes the Earth can be seen as a blanket. The Earth absorbs the sun's rays during the day and heats up. After the sun sets, the Earth emits this heat back into the atmosphere. Greenhouse gases have the effect of making this blanket thicker and even more effective at retaining the heat emitted overnight. This ultimately causes average global temperatures to rise with yet undetermined environmental impact. Unburned volatiles are among the worst greenhouse gases. The first category of unburned volatile is from unburned hydrocarbons. A simple burner tuning is normally enough to eliminate this source almost entirely. Other volatiles can be emitted from industrial processes. Afterburners are an effective tool at eliminating this source. Landfill capture stations and minimizing system vents are all proving effective at eliminating unburned VOCs from entering the atmosphere. Sulfur, carbon, and nitrous oxides have become the modern-day compounds at the forefront of emission standards. This is for very good reason, as they all contribute not only to the greenhouse effect, but also acid rain and smog formation. Sulfur dioxides, and trioxides to a lesser degree, are compounds that are produced directly from fuel-bound sulfur molecules. Little can be done to eliminate them once they are formed. Expensive scrubbing technology is available, but at very cost-prohibitive levels. The simplest solution is to use fuels like natural gas and propane that have much lower sulfur concentrations than traditional fuel oils. Condensing of sulfur dioxide causes severe corrosion in industrial equipment. It is also one of the main causes of acid rain. Moving away from sulfur dioxides, the next important oxide group would be carbon monoxide. Known as a silent killer, carbon monoxide is a colorless, odorless, transparent molecule that is highly effective at irritating our eyes and lungs. Asphyxiation is a severe risk when dealing with carbon monoxide, even in low concentrations. Although sometimes carbon monoxide is generated from the process, it is normally a very strong indicator of incomplete combustion. Governments have implemented strong regulation regarding its acceptable emission levels because carbon monoxide formation is highly controllable. There are three major ways to help eliminate the generation of carbon monoxide within a given combustion system. 1. Burn lean. 2. Burn hot. And 3. Keep the combustion products in a hot combustion chamber for as long as possible. We will discuss carbon dioxide as an emission only because it is the predominant greenhouse gas. It is all our responsibility to be as conscientious as possible regarding the environment. Burning hydrocarbons will always result in the production of carbon dioxide and water. The chemistry is what the chemistry is. The only way to eliminate carbon dioxide is to eliminate the carbon from the fuel itself. This is why alternative fuels and efficient use of the fuels we consume is essential to reduce our overall environmental impact. No discussion about environmental oxides would be complete without the notorious nitrous oxide family. Both nitrogen monoxide and nitrogen dioxide are grouped together under the NOx banner that is stated repeatedly in industrial combustion. NOx generation has become extremely important in modern society, as it is not only an eye and lung irritant, but smog formation in all major cities is a visual reminder of its impact on all of us. The gray-red cloud that hangs over most large cities is a direct byproduct of NOx molecules in the atmosphere. NOx is formed via three independent mechanisms. 1. Fuel-bound nitrogen. 2. Prompt formation. And 3. Thermal mechanisms, also known as the Zeldovich mechanism. Of the three mechanisms causing the formation of NOx during the combustion process, the first two are minor in nature when compared with the Zeldovich mechanism. Fuel-bound nitrogen NOx formation can only be mitigated by using fuels that do not contain nitrogen. Moving away from coal and other heavy oils can significantly reduce this minor contributor even further. Prompt NOx formation comes from the bonding of nitrogen with hydrocarbon-free radicals. This mechanism is only of concern in sub-stoichiometric systems and is of limited concern in modern-day furnaces. The Zeldovich mechanism for NOx formation is more commonly referred to as thermal NOx formation. As the name implies, this mechanism is directly linked to the temperature of the combustion process. Graph A at left clearly demonstrates that as the system temperature is increased, so does NOx formation. The main driver here is the molecular dissociation of atmospheric nitrogen. Graph B shows that excess oxygen initially increases NOx formation. As the amount of excess oxygen crosses the threshold of 7 to 8%, the formation of NOx begins to lower. As we have already learned, most regulatory bodies are most concerned with carbon monoxide and NOx emissions. Unfortunately, we have also learned that what helps lower carbon monoxide emissions ultimately increases NOx emissions. The curve at right clearly demonstrates the emissions dilemma facing modern burner designs. One needs to burn hot to minimize carbon monoxide production, but this dramatically increases NOx formation. So, what can be done? Tight control of the fuel-air ratio using fully metered systems, higher gas and air pressures increasing mixing power, injecting of secondary or tertiary air, increasing dimensions, both diameter and length, of the combustion chambers. These are all tools used by the modern combustion engineer to find the Goldilocks zone for emissions. As with the compromise between carbon monoxide and NOx formation, overall system efficiency is also a compromise between two competing forces. For thermal efficiency, we want to burn hot, but in order to minimize emissions, burning hot is not always the best solution. Without getting into the complex mathematics regarding system efficiencies, typical industrial combustion systems run most efficiently at slightly lean combustion ratios. We would typically see systems with approximately 15% excess air as the target for optimum operation. This point tends to minimize carbon monoxide and NOx formation while maintaining thermal efficiencies as high as possible. So, what have we learned? Quebec regulation stipulates limits of 400 ppm for carbon monoxide and 50 ppm NOx emissions for industrial applications. Emissions can be divided into three major groups: particulates, unburned volatiles, and oxides. We know that carbon monoxide is reduced at high temperatures. We know that NOx is increased at high temperatures. And we know that efficiency is a compromise between responsible energy use and environmental emissions.